So we've been talking about kinetic isotope effects, and this is basically where you do a reaction with hydrogen versus deuterium at a particular carbon, and then you measure the rates of the reaction, and then that's the easy part. The tough part is interpreting what the results mean, and so I'm trying to give you a framework that will help you understand what the kinetic isotope effect means. I want to dig into it in a little bit more detail than is typically done in undergraduate classes, but not so much that you get overwhelmed. So we'll see how we strike that balance. And as we do so, we'll talk about what a primary kinetic isotope effect versus a secondary one, what normal is versus inverse. But for right now, have this idea that if the atom or bond where you made a substitution of hydrogen versus deuterium is not involved in the rate transition state of the rate determining step, or is not in some form of change during that transition state, then you expect there to be not really much of an isotope effect at all. Okay, so we had started our discussion last time talking about how carbon hydrogen versus carbon deuterium bonds have different 0-point energies, and we'll define what that is in just a second. But before we do that, I just want to give you a little bit of background. You remember in chapter 7 when we talked about rate, if this is the rate constant for a reaction that has hydrogen at a particular carbon, then presumably that rate constant comes from some pre-exponential factor. This is using the Arrhenius equation, then raising the number E to the minus activation energy for hydrogen. Okay, that's by activation energy for hydrogen, I mean activation energy for the molecule where hydrogen is at a particular position. And then this will be divided by and for our purposes today, we're going to be talking about individual molecules, so we'll use Boltzmann's constant instead of the gas constant, and then temperature. Similarly, we could write the same equation for the rate of deuterium, some pre-exponential factor times the number E raised to the minus activation energy for deuterium over Kb times T. So now with a little bit of logarithmic properties, we can see that the ratio, the kinetic isotope effect, the ratio between the rate constant for hydrogen versus deuterium is equal to the exponential of minus activation energy for hydrogen divided by Planck's constant times temperature, and then we'll do the same thing on the bottom, but for deuterium. I'm just doing the algebra at this point. And then maybe you remember that when we divide exponentials by each other, there's property of exponents that we can do here. So this is exactly the same as just saying, and I've canceled out the pre-exponential factors, which are the same. This is the same thing as saying dividing two exponents is like subtracting, dividing two exponential expressions is like subtracting the exponents. I can't remember what the rule is in math, but sort of some of you are nodding your heads, so you sort of get it. So that's the same as subtracting those two terms inside the exponential. And, or in other words, the kinetic isotope effect that we observe is going to be related to the difference in activation energy for hydrogen versus deuterium. Okay, so this is useful. We expect a positive kinetic isotope effect when the activation energy for deuterium is greater than the activation energy for hydrogen. Okay. And the bigger that difference, the bigger the kinetic isotope effect that we're going to observe. All right. So we want to talk about how these numbers, how and why those numbers, those activation energies are different. Okay. And this is related to the idea that, and this is overly simplistic because this is imagining a reaction where we go from a bond being completely formed to a bond being completely broken. And you can see that getting up to that complete bond breaking has a larger energy for carbon-deuterium bonds than for carbon-hydrogen bonds. But we need to figure out why these 0-point energies are different and how these activation energies vary and why they vary with deuterium versus hydrogen. So let's talk a little bit about bond vibrations, because 0-point energy comes from quantized bond vibrations in a potential energy well. So this is an example up here of a potential energy well, and here I'm showing you the lowest bond vibration energy levels for hydrogen versus deuterium. Okay, so this is going to be a little bit of P-Chem, which we are not going to justify based on first principles, but in the end is going to give us some important background. So if you have a particular bond vibration, we're going to let this E equal, this number is going to be the vibrational energy. Energy of a bond vibration, one of the quantized bond vibrations, where n is an integer from 0, 1, 2, etc. That's the quantum number for a vibration. Individual bonds have lots of vibrational modes. We're just talking about one of them for now. That energy can be shown in ways that I don't know to equal the quantum number plus 1/2 times Planck's constant times the vibrational frequency. Where does the 1/2 come from? I got nothing. Maybe some of you remember. But notice that even when the quantum number equals 0, our bond vibration still has energy. In other words, even at the lowest energy point for a particular bond, there's still some wiggling. And that's what we call the 0-point energy. Okay, so now we should talk about why the 0-point energy might be different for hydrogen versus deuterium. Okay, and that's the same thing as asking why is vibrational frequency different for a CH bond versus a C-deuterium bond. Okay, so now we'll go to some stuff that probably you learned in a physics class a long time ago. And this has to do with the fact that bond frequency depends on a couple of things. First, it depends on K, which is, actually we're going to call it F because we got too many Ks. F, which is a force constant. That's a term that describes how stiff a spring is, or in other words, how strong a bond is, or what its environment is, where stiffer springs vibrate more rapidly. And then it will also depend on the masses attached to the spring. So we're envisioning a carbon-hydrogen bond as carbon here, spring, and hydrogen here. And so the vibrational frequency for hydrogen in this carbon-hydrogen bond is going to be equal to, and again, this isn't something to memorize, but just to be aware of, 1 divided by 2 pi. We don't really care about that. And then square root of force constant F times the mass of carbon times the mass of hydrogen divided by the mass of carbon plus the mass of hydrogen. Okay? So now let's do the same thing for deuterium. And the force constant we'll assume is the same, mass of carbon times mass of deuterium divided by mass of carbon plus mass of deuterium. Okay? So let's compare these two vibrations, shall we? Because if we can compare the vibrational frequency for hydrogen versus the vibrational frequency for deuterium, we can get an idea of what these energy differences are. And if we know the energy differences, we can predict what the kinetic isotope effect is. Okay? So if you divide these numbers by each other, we won't do the algebra, but the constants cancel out. And you end up with, let's see, mass of carbon times mass of hydrogen divided by mass of carbon times mass of deuterium, right? Times mass of carbon plus mass of deuterium divided by mass of carbon plus mass of hydrogen. Okay, and of course, let's see, masses of carbon cancel each other out. And let's just get an idea of what the numbers are, right? For mass of hydrogen, we're dealing with something like 1, right? Mass of deuterium, 2. And then for carbon plus deuterium, what is that? 12 plus 2 is 14 divided by 12 plus 1 is 13, something like that. Have I screwed something up? I think. Oh, I thought I did something in my head that was wrong. So I apologize. I divided by a fraction and forgot how to do that. Okay. So up here is mass of carbon plus mass of hydrogen. Down here is mass of carbon times mass of hydrogen. I'm sorry about that. Very remorseful, but I can't go back and change it. So there you go. Maybe I'll go back and edit this part out of the video so I sound smarter than I am, right? Okay, so if we do that, we have over here mass of carbon plus mass of hydrogen divided by mass of carbon plus mass of deuterium, and then mass of carbon times mass of deuterium divided by mass of carbon times mass of hydrogen. All right. Mass of carbon cancels out. We end up with the fraction that looks something like this. 13 divided by 14 times 2. Okay? And the actual identity of that fraction isn't necessarily important. What I mean to say is that if we run these numbers out, we can calculate what the energy difference is for hydrogen versus deuterium. Okay? And therefore, yeah. So if you make the assumption that the difference in energy of activation for hydrogen versus deuterium is related to this difference in vibrational energy, and you remember that the vibrational, so energy of activation for deuterium minus the energy of activation for hydrogen should equal, based on that diagram above, that should equal the difference in vibrational energy for the 0 point for hydrogen minus the difference in vibrational energy for the 0 point for deuterium. And so given a typical carbon-hydrogen bond, and given this ratio of vibrational frequencies, which really just depends on the ratio of the masses, we can calculate that the maximum kinetic isotope effect that we would expect should equal about 7. Okay? So that's a case where carbon-hydrogen bond breaking is basically complete at the transition state. And I got this number by using this ratio, by making an assumption of what the carbon-hydrogen vibrational frequency should be. You can do that from an IR experiment, right? And then Planck's constant, and then this equation here, and assuming what the temperature is. And yeah, at about room temperature, you expect if there's complete carbon-hydrogen bond breaking in the transition state, you expect a maximum effect of about 7. Okay? So you're doing a kinetic isotope experiment. Whoa, I get a very large, and so a kinetic isotope effect of 7 is large. Okay? And we would call this, because of its size, we would call it a primary normal kinetic isotope effect. Okay, but naturally there's always exceptions to this process. Okay, and the complication occurs because not all transition states have complete bond breaking in them. In fact, very few have complete bond breaking in them. So we're going to examine a few scenarios that give us a sense for when to expect kinetic isotope effects and when to not expect kinetic isotope effects. All right. Questions so far, though, before we move on? Okay. All right. Concern number 1. Is going to be the similarity of the transition state structure to starting material structure. All right. So let's imagine, and we'll use sort of Hammond postulate to think about this. Let's imagine a very exothermic reaction where the transition state is very close in structure to the starting material. Here's your transition state, here's your starting material. All right? And of course, on this axis, we have energy. And on this axis, we have reaction coordinate. And usually that reaction coordinate is related to a particular vibration. As an example, suppose we have a reaction where A is bonded to hydrogen, and then B comes in and removes the hydrogen from A. So in the end, we have this. And then the transition state involves some intermediate where the bond is partially broken and the new bond is partially formed. The vibration that corresponds to the reaction coordinate, what do I mean by that? Well, as the reaction progresses, we expect A to move this way, we expect hydrogen to move this way, and we expect B to move this way. This is sometimes how people represent sort of the centers of vibration, and this is hard to envision unless you actually make a model and see it, which we could do. But the reaction coordinate involves A going this way, H going this way, and B going this way. And actually, that is a vibrational mode. And going through the reaction just involves getting to the point where that vibrational mode gets you over the transition state and to the product. Okay? But there are lots of other vibrational modes that do not contribute to the reaction going forward. It turns out the vibrational mode that leads to the reaction going forward, this one does not contribute, that vibrational frequency does not contribute to the kinetic isotope effect at all. Instead, other vibrational frequencies do. And we're going to imagine that these vibrational frequencies come from potential energy wells that exist perpendicular to this reaction coordinate. So we're going to think about a three-dimensional energy landscape. Motion along this direction takes you through the reaction. Motion in any other direction takes you up a potential energy barrier. And so if we took a slice, just imagine a plane here taking a slice of the three-dimensional reaction coordinate energy diagram, what would that look like? And I'm going to use maybe blue, no, purple, no. I don't know what we should use. Pink for the potential energy well at the starting material. Okay, so from our perspective, this is not the reaction coordinate. It's some other kind of vibration that doesn't lead to the reaction. An example might be this particular vibrational mode where hydrogen's in the middle, B is here, A is here, and we're going in that direction, which happens too. All right, so, and what we're saying is as these distances change, we either go up or down that well, and then there are quantized vibrational frequency levels for hydrogen versus deuterium here. In, I guess, blue, I'll do the 0-point energy for deuterium. And in orange, I'll do the 0-point energy for hydrogen. Okay? So there's questions so far. This is kind of important. We're in the two-dimensional energy diagram, we're ignoring all other motions except for the one that leads from starting materials to products. But we're recognizing that along that trajectory, we can take a slice perpendicular to it and see energy wells. And then, so what we're doing is, I don't know if you remember when we looked at the mountain pass, we're looking at the saddle of a mountain pass, and here's the pathway over that saddle. But here we're focusing on the vibrational energy levels that are created by that saddle. Okay. Sorry, you with me okay so far? Ish, a little bit. Questions? All right. Now, we said that the transition state structure, in this case, because the reaction is highly exothermic, by the Hammond postulate, because the transition state and starting material are close in energy, they have to be close in structure. Okay, and therefore in vibrations. So if we take a slice here, this is starting material, let's take a slice through the potential energy surface at the transition state, and let's examine what we would see there. All right, so we'll draw that slice here. Here is the transition state. Now I guess we're using pink for the surface that's perpendicular to that. So now, if the transition state is similar to the starting material, the vibrational energies in the transition state should be similar to the vibration energies in the transition state. In other words, the 0-point energy for deuterium is going to be about, relative to the 0-point energy for hydrogen, is going to be about the same. Oops. Okay. So now let's look at energy of activation for hydrogen versus deuterium. So the orange arrow is going to be, I'm going to make a, oops, that's not orange, is it? I'm going to make a dotted line from here. I actually am going to just shift everything down so where I put that energy well is at the top of that transition state. And then I guess I need to do the same thing here where I put this energy well is at where the starting material is. Okay? So the activation energy for hydrogen is right here. It's the energy difference between the 0-point energy for hydrogen in the starting material and the 0-point energy for hydrogen in the transition state. Similarly, the activation energy for deuterium is right here. It's the difference between the 0-point energy of deuterium in the transition state versus in the starting material. Now, because the transition state and the starting material are similar in structure, I'm going to highlight in, I don't know what color we should choose, running out of colors. I'm going to use purple and sort of highlight this space between hydrogen and deuterium. That's my difference in 0-point energy in the starting material. Here's my difference in 0-point energy in the transition state. Notice the way we've drawn that, those energy differences are similar, right? In fact, they're, as we've drawn it, they're basically the same. Now, we could do some arithmetic to demonstrate that this is the case, but it turns out that the difference in energy it turns out that if these 0-point energy differences are the same, these activation energies are the same too. And I don't know, I mean, we're not using rulers or doing arithmetic, but basically the same, right? So just, do I need to prove that to you with arithmetic, or will you accept it based on inspection of the drawing? Okay, so it's an important lesson, right? If a bond is similar in the starting material and similar in the transition state, then activation energies for hydrogen versus deuterium are about the same. So that's what we've observed here. Activation energies for hydrogen and deuterium are similar because the transition state and starting material are close in structure. Now go back to what we concluded from above. The kinetic isotope effect is equal to, or depends on, the difference between those activation energies. So if those are the same, this goes to 0, and my kinetic isotope effect is what? It's about 1. Okay? So that's one situation where I cannot observe a kinetic isotope effect, even if a bond is changing during a reaction, because it's not any different in the starting material. It's not very different in the starting material than it is in the product. All right? Questions?
So we're saying that ED minus EH, that's about 0.
Yeah. Yeah. Because of what we're saying here, this would be 0. Yeah. All right. And there's other scenarios you can imagine. If the reaction were very endothermic, and if the transition state instead resembled the product, but the bond strength and vibration in the product were pretty similar to the starting material, we might also expect to not see a very good kinetic isotope effect. I could draw that for you if you wanted, but what it would show you would be just another situation in which you have, in this case, it would be starting material and product. Starting material and transition state and product. And what we're saying is that if the product and the starting material have similar bond strengths and similar 0-point energy differences, and if the transition state resembles the product, then you're still going to have a basically minimal difference in activation energies and not observe a strong kinetic isotope effect. So the principle you can extract from this is conclusion number one is very early. What do we mean by early? That is starting material like. Or very late. What do we mean by that? Very product like. Very early or very late transition states have small kinetic isotope effects, if any. You will sort of expect the kinetic isotope effect to be 1. Okay? So what's a situation where it might be huge? Imagine a reaction where the transition state doesn't closely resemble starting material or product. Okay. Energy here. On this axis is going to be reaction coordinate. I'm not going to specify what the reaction is, but we're going to say, okay, here is a reaction where the transition state, and we don't really care whether the reaction's exo or endothermic, starting material, product. We're not going to worry about that difference in energy. But let's imagine, remember how I said that if the reaction is A attached to H going to B, and well, I guess this is our starting material, this is our product, and the reaction coordinate represents motion of H toward B and motion of A away from H. Then let's look at and let's consider that we're taking a slice of the transition state, looking at the following, I need to shrink this, at the following vibration. So we're going to, okay, in pink is going to be this vibrational energy level, and this is going to represent what's called a symmetric stretch, where hydrogen is here. Got to make sure I get this right, because this is stuff where I'm somewhat weak, where hydrogen is here and B is here and A is here. This would be a stretch where A and B do most of the moving and hydrogen moves a little bit. It may move back and forth, not necessarily in time with A and B. We call that a symmetric stretch. Okay, and here Hmm. And so here we have the 0 point energy. Oops. Here we have 0 point energy for deuterium. Here we have 0 point energy for hydrogen. Now, let's imagine in the transition state that rather than look product-like or starting material-like, that hydrogen is basically evenly shared between A and B. So this is the transition state structure. If that were the case, if the bond distances are similar and if the distances between nuclei are similar and bond lengths, well, are similar, bond strengths are similar, you would then expect the stretch to be mostly about B and A moving, whereas hydrogen is going to be in the middle doing nothing. Does that make sense? Over here in the starting material, hydrogen isn't evenly shared, and so it's going to be vibrating sort of this way. I think I want to erase that. This would be like observing bonds stretching between hydrogen and A, and then B is hanging out over here. But in the transition state, because hydrogen is evenly shared between the two, hydrogen is not moving. If the spring is mostly A and B and not hydrogen, then what does that say? That says as we take a slice of that energy diagram perpendicular to the reaction coordinate and we look at that potential energy well, and if we conclude that hydrogen isn't moving, then it actually shouldn't matter too much whether it's hydrogen versus deuterium. Okay? So in this transition state where hydrogen's evenly shared, there basically is no 0 point energy difference. Because in this transition state, we're imagining hydrogen is not moving. So let's see what that does to our activation energy. And again, I may need to shift some things around to get things at reasonable relative heights. Okay, close enough. So here is the energy level, 0 point energy for hydrogen in the transition state. Here it is for hydrogen in the starting material. That then is our activation energy for hydrogen. In contrast, here is our 0 point energy for deuterium in the transition state. Here is our 0 point energy for deuterium in the starting material. What do you notice now about those activation energies? Which one's bigger? Deuterium, right? As we've shown it here, because there's not a big 0 point energy difference in the transition state, activation energy is higher for deuterium than for hydrogen. And because our rate constant ratio depends on the difference between deuterium and hydrogen activation energies, if this number is positive and large, then we expect this ratio to be greater than 1. Okay? So, some of your thinking about kinetic isotope effects has to take into account bond vibrations. But here's another interesting conclusion. You can use the kinetic isotope effect as a kind of reaction coordinate for your carbon-hydrogen bond. If the kinetic isotope effect is equal to 1, that means that bond breaking is either not begun or perhaps almost complete in the transition state. whereas a large kinetic isotope effect means that you're somewhere in between that. Okay, so unlike reaction coordinates that go from 0 to 1 and it's sort of percent, using kinetic isotope as a effect as a reaction coordinate is kind of like you start out at 1 here, you get close to 7 if your transition state's in the middle, and then you go back to 1 over here. But in any case, that can give you a sense for not only is your carbon-hydrogen bond changing in the transition state relative to starting materials, but how far along the reaction that change is happening. All right. Is that clear as mud? What questions do you want to ask? I've tried to make this way less technical than it is in the text, and even than it is in my notes, because I looked at my notes earlier and I was like, whoa, what's all that about? Okay. So let's talk about secondary kinetic isotope effects. These are small but predictable. And again, we're going to have to delve a little bit into the world of bond vibrations. Okay, so I'm going to copy down this stuff. And we're just going to remember that the difference in bond vibrations tells you something about the difference in energy of 0 point energy for various bonds. Okay, so and I think probably for our discussion we're just going to need this. All right. So in our previous discussion, we basically ignored this force constant. But for some kinds of reactions, so maybe we'll call this complication number 2. I'm not sure what we're on. Maybe we'll call it complication 3. Who knows? It's another issue. We'll call this changes in CH bond hybridization. Okay. So everything we've done so far has been based on the assumption that the force constant is not very different, or we can sort of neglect it in terms of thinking about 0 point energy. Let's think about the frequency of vibration for hydrogen in, say, the starting material versus hydrogen in the product, and whether the force constant in the starting material can be expected to be different from the force constant in the product. And then we'll use the Hammond postulate to figure out where the transition state is in product versus starting material. So let me show you a couple of examples of bond vibrations that do change with hybridization versus bond vibrations that don't change very much with hybridization. Okay, so for an sp3 carbon-hydrogen bond, here's the carbon-hydrogen bond that we're interested in, and then here are the other 3 groups. They're not necessarily methyl groups, we're just ignoring what they are. There is an out-of-plane bend that involves sort of everything else staying stationary, and then this hydrogen wagging outwards towards us, and then wagging backwards away from us, swinging in and out of the page. All right, so this is fishtail action. All right. Now let's examine the same kind of thing for an sp2 hybridized carbon-hydrogen bond, all of these atoms are in the plane, and we're going to consider, again, wagging of this carbon-hydrogen bond out towards us and then back away from us. Again, fishtail action. And let's consider what we tend to observe. So, and we can actually see these vibrational frequencies in the IR. For an sp3 hybridized carbon-hydrogen bond, this out-of-plane bending shows up at about 1350 wave number. Wave number is a way to express wavelength that is proportional to frequency, so higher numbers mean higher energy. Did you have is that your question, Alvaro? No? Okay, sorry. However, for the sp2 hybridized carbon-hydrogen bond, it's a much lower frequency vibration, and therefore a much lower energy vibration. Why is that the case? Well, sp3 hybridized carbons are more sterically crowded. As this hydrogen wags in and out of the page, it's going to start to bump into these other groups, whereas because the sp2 hybridized carbon is planar, there's really not a lot to bump into as this hydrogen wags in and out of the plane. Okay? So one of the things that we could say is that the out-of-plane bend for an sp3 hybridized carbon has a stiffer, larger force constant, whereas the sp2 hybridized carbon-hydrogen bond vibration out of plane has a weaker, smaller force constant. Okay? So what's that going to do if we look at differences in energy of that vibration from product versus starting material? If the force constant decreases as I go to product, my vibrational frequency is also going to decrease. So now before we were considering where the transition state lies along the energy diagram, whether it's too product-like or too starting material-like. But now we're going to consider how does this force constant change as I go from starting material to transition state. Okay? I don't want to get this wrong. Okay, so if you were to imagine what a kinetic isotope effect would look like, it's going to take too long to do the math that's going to help us figure this out. The theoretical max for going from an sp3 hybridized carbon to an sp2 hybridized carbon, where a lot of that rehybridization has happened by the time you get to the transition state, is around 1.4. Okay, and that we would call a normal secondary kinetic isotope effect. The vibration gets weaker in the transition state than it does in the product. That's going to result in a kinetic isotope effect, but it's not going to be very strong. Going from an sp2 hybridized carbon to an sp3 hybridized carbon-hydrogen bond will give you a kinetic isotope effect that is less than 1. And the range here, it again tends not to be very large, but this would be called an inverse kinetic isotope effect. Now we could go through and do the same analysis as we've done up here to sort of rationalize why going from sp3 to sp2 has a greater than 1 kinetic isotope effect, but why going sp2 to sp3 has a less than 1 kinetic isotope effect. I don't know that that's worth our time. I will put it in the notes that I post so you can look at it if you're interested. If you were content to just memorize this, you're welcome to do that too. I tend to like to see things derived for myself because then I feel like I understand it, at least until I forget how to derive it again. But that being said, you don't necessarily need to know things from first principles to be able to make sensible predictions. So next time I'll show you some data, the results of an experiment that can give insight into mechanism by looking at the presence or absence of this kind of kinetic isotope effect. All right, have a good weekend. We'll see you on Monday.